Hello, everyone. Hello, and welcome to the last plenary of OR65 as we're winding down the conference. Not only we have the plenary, but we also have parallel sessions right after the plenary. I'm even presenting in one of those, so there you go. You know, the fact that I'm co-chair of this conference didn't give me a preferential slot to the schedule, but I hope to see you as many as possible at the plenary, at the parallel sessions after this, the plenary, and then we also have some tea and coffee and biscuits or something along these lines at 4:30 to reward those who stayed the course. So before we start with the actual plenary, I hope you enjoyed the dinner last night. Have a few photos of the lovely place we were, and that was us, and that was me this morning. I think I still look like this, but Kathleen looks fantastic, and Kathleen has something to tell us about next year's OR Society conference.
Thank you. So the announcement is that next year we'll be heading to Bangor University. The dates for OR66 will be the 10th to 12th of September. So pop it in your diaries. We hope to see you there. Thank you so much again for joining us in Bath. Thanks again to Christos, Meli, Mitu. It's been awesome working with you all. Next year, also, I can announce that the co-chair for OR66 will be Mozab Bazargani, who works at Bangor University. And yeah, we look forward to hopefully seeing you next year. Thank you.
Well, I will definitely be there enjoying an OR Society conference without having to co-chair it. So without further ado, let me click once more. It is my pleasure to welcome our plenary speaker. Now, I'm Greek, I'm used to difficult names. I know Erik for 15 plus years, but I have to admit, your surname, Erik, still puzzles me a little bit. So welcome to Professor Erik Demeulemeester.
Okay, pretty good. Right.
For someone called Vasilakis, that's the better. Who is a full professor in the Research Center for Operations Management at KU Leuven in Belgium. Those who haven't been to Leuven, I highly recommend. It's a beautiful, beautiful part of the world. I was there only about a month ago. He's currently the chair of the Department of Decision Sciences and Information Management at the Faculty of Economics and Business of the KU Leuven University. He earned his degree in business engineering, his first degree, in 1987, his words, not mine, and also an MBA and a PhD, all from the same university. The title of the thesis was Optimal Algorithms for Various Classes of Multiple Resource-Constrained Project Scheduling Problems, and that should give you a hint of what this plenary will be all about. At present, he's a full professor from 2000 onwards and currently teaches on a course on project management scheduling, doctoral course on combinatorial optimization and local search techniques, as well as a seminar on production logistics. His main research interests are situated in the field of project scheduling and healthcare planning, and this is where I got to know Erik over the years, and he has published many, many papers in these topics, as you can expect. He is currently on the editorial board of VJOR, the Journal of Scheduling, Computers and OR, and the European Journal of Industrial Engineering. Finally, he served on Euro Conference program committees and is a core jury member of the Euro Excellence in Practice Award. And perhaps where we got to know each other, he has organized the health-related working group conference back in 2009 in Leuven. That was my first chance, I think, to visit that place there. So without further ado, Erik, thank you very much for coming here, and we look forward to your presentation.
Okay. Okay, thank you, Christos, for the nice introduction, and welcome all. So today I will be talking about proactive reactive resource-constrained project scaling problem, or RCPSP as it's better known. And perhaps I should best start with a simple example. So here we have an example where we have a number of nodes, the rectangles that you see, where in each node first you have the activity number. You see there are 7 real activities here. The second number is the duration, the deterministic duration of that activity. And the number at the bottom line is the resource requirement, the number of operators that you need, the number of machines that you need or tools that you need. And there are 5 available, as you see on the top left. Okay? This is just not a particular problem. It's a problem I created more than 30 years ago for a particular reason, because at that time I was studying a procedure by Christofides, Alvarez, Valdez, and Tamarit. And I had some hunch that they were missing some of the schedules. So I created this problem where the particularity is that it has only one optimal solution, namely this one. Okay, so you have to puzzle it a little bit. And I could show that this solution method did not find this one. So at that time, Jim Patterson happened to visit us in Leuven. And so I was doing this during the weekend. And on the Monday, I was mentioning this to my promoter, Willy Harulen, and to Jim Patterson, who were visiting. And it happened so that Jim Patterson obtained a code from Christofides, Alvarez, Valdez, and Tamarit, but that was in Bloomington, so he mailed this, it took a while, to Bloomington, to Indiana University, and the next day we got a reply that indeed they were finding a solution of 8, which was not the optimal one of 7. Okay, so we were very happy, and this delivered us a paper in eJOR at the end, so it was a good effort, a good spending of my weekend at that time. Okay, so here you also see a tool which is RESCON, which we developed at the university and during one of the projects, and it's a nice educational tool. If you want to teach some course on project management, project scheduling, you just type in RESCON KU Leuven and you will immediately find this tool and think it's helpful. Here you can also see a number of heuristics which are applied to this problem. And here you see that, well, you can find 7, and even some of the heuristics find the 7, the optimal solution. But if you are unlucky, you can also have a solution of 12, okay, which is almost double the solution, which is quite unlucky. So over time, many people have researched this problem. And in my PhD, as Christos mentioned, I looked for a very efficient branch and bound algorithm for this problem, which in the end I think I did. But also afterwards, LP-based optimizations, constrained programming optimizations have been performed. And in fact, you can solve this problem pretty efficiently. There are some problems of even 60, 70 activities that you cannot solve optimally, but then there are very good heuristics, okay, also meta-heuristics for it. So let's assume that this problem is relatively well solved. So we are able to find good optimal or very good heuristic solutions for it. So over time, other researchers and our group has went into other problems which are related, which are extending this one. And today I want to mention one of them, which we call the proactive reactive resource-constrained project scaling problem. Okay. So what is the purpose? Well, in the first phase, as the name suggests, we will have a proactive phase where we try to construct a baseline schedule which is as insensitive as possible to do anything that might happen in the future. So here today we will be looking at stochastic durations, but we have also done research on resources breaking down or having to have changes in activities or changes in the resources that are needed. So what we want is a baseline scale that is as insensitive as possible to anything that might happen in the future. Okay? So we want to protect our schedule as much as possible, perhaps thinking of, well, there will never be deviation, that's one way, but also when there is a deviation, how can we react? And that's where the second phase comes in. So sometimes it's impossible, well, either you are very pessimistic, or otherwise you will always have some probability that some deviation shows up, that some activity needs to be started, cannot be started because previous activities are still proceeding. So at that time, you want to make sure that your reaction is as cheap as possible. And in fact, as I will mention on the next slide, that the overall cost, the expected cost of scheduling this project and reacting whenever needed is as minimal. So what will happen is that every time there is a distortion, there is an activity taking longer and some other activity cannot start at that time, then we have to react, there will be some cost involved, and in the end, we might do this a couple of times, and this will create a realized schedule. Of course, this reaction This will take some administrative effort. You might have to phone up your subcontractor and say, well, we planned that in the week of 13th to 20th of November, we were planning you to come in to work for us, but sorry, we were not able to complete the previous activities in time, so it has to be delayed. So you can imagine that this will be some cost involved. It might also be that you want to rent some heavy equipment that you don't own in your own company. Well, again, you want to have some timing for that. So that's where the baseline schedule comes in handy. Okay. How do you create this baseline schedule? Well, typically, you have a two-phase approach. In the first approach, what you will do is you will take some deterministic durations, and you will run some code, some branch and bound code, some meta-heuristic, which will provide you with the optimal or a very good solution. And then you will try to make this schedule more and more robust, and there are two particular ways that are possible. One is by looking at robust resource allocation, and I will show this on the next slide. We'll try to devise how the resources are passed from one activity to the other. And secondly, you all know this, you can introduce time buffers. I'm taking a train this afternoon, but if I would be flying from Bristol, for instance, to London, and then from London to Brussels, if there was a transit time of only 45 minutes, then I don't think that the buffer would be long enough. So we are all used to introducing buffers. This is also what's been suggested here. Okay? So now let's look at these two. So here again, an example, same format somewhat. You have 4 real activities, 1 to 4 here. Activity number first, then the deterministic activity duration for the moment. At the bottom, you have the resource requirement. Okay, so for instance, activity 3, having a duration of 2 days, for instance, and needing 2 resources while the availability is 4. It's traditional in our field that we have a dummy start activity, just to indicate the start of the project, and a dummy end activity here. Okay, that makes it easier for some of the algorithms, but not necessarily required. Okay. Now, if I would put this in Rescon, the software that I just shown before, you could come up with some schedule like this. This is an optimal schedule for the problem at hand. And in fact, I can easily show that it's an optimal schedule, because if you look at this problem, okay, we can define some what we call forbidden sets. Forbidden sets are combinations of activities where there is no presence relation in between, but if they would be scheduled in parallel, they would violate the resource constraints. Lots of words to say. Well, if you look, for instance, at activities 3, 1, and 2, there is no presence relation between any of them, so you could schedule them in theory in parallel. However, they are requiring 2 plus 1 plus 3 is 6 units, okay, which is violating the resource constraint. So you cannot schedule them together. In fact, we are not really that much interested in the forbidden sets, but in the minimum forbidden sets. For instance, in this case, if we have 3, 1, and 2, we could omit activity 1 and still have a forbidden set. Activities 3 and 2 have no presence relation in between them, and they require 2 plus 3 is 5 units, only 4 are available. Okay? So that's the minimum forbidden set. Similar thing when we look at the back end, activities 3, 4, and 2 together require 6 units also, but again, we can omit activity 4, so we have only one minimum forbidden set. And then the theory says that if we can break this minimum forbidden set, then we can create an optimal solution where we don't have to look at the resource constraints anymore. So the minimal forbidden set being 2, 3, solution being, well, we schedule either 2 before 3, so we have an additional what we call resource arc, or we schedule 3 before 2, the opposite way. And indeed, you see in the solution that we have here, we are scheduling 2 before 3. You cannot do less than this, so we have a duration of 2 plus 2, so that's 4, that's the optimal solution. Okay. I'm presenting this solution in this way now because we can also think of this robust resource allocation. And if you look at it, we can think of the individual resources and how they are passing from activity to activity. For instance, if we have 4 operators here, these might be Adam, Bruce, Cynthia, Diana. Okay. If you look at Adam, for instance, he works first on activity 1 and then switches to activity 3 at time 2. That's a plan at least. And then he might work on some other things. Bruce, I was saying, is working first on activity 2, then activity 3. Cynthia, 2, then 4. And Diana is working only activity 2, and then later might be going on holiday, or might be following courses, or might be working on different project, whatever. But hopefully we can finish in time. Okay? In fact, if you look at how these resources are transferred from one to another, what we see in this representation is that, well, Bruce working first on activity 1, and then activity 3. If now activity 1 would take one period longer, what would happen? Well, Bruce would work for 3 days on this activity 1, and only then can move to activity 3, so that it will be delayed for 1. So you will lengthen the project. But also, if activity 2 or activity 3 is lengthened, you would automatically lengthen the project. Okay? So in fact, this is not a very good way of allocating your resources. What is a better way is the one that you see here. In fact, we have the same schedule. We have the same starting times for each of the activities, so the schedule is perfectly the same. However, the allocation of the resources is somewhat more clever. Of course, it's a small problem, it's relatively easy to do. But here you see that now Bruce is working first on activity 1, and then on activity 4. Okay? But this does not create an additional problem, because you already have a presence relation 1 before 4. So 4 had to wait anyhow on activity 1. Okay? And now if you look at Bruce and Cynthia, both of them are working on activity 2 first. As soon as they are finished, they can move on to activity 3. Okay, we are introducing an additional resource arc, but as I just mentioned, because of the minimum forbidden set, we cannot do any better than this. So we have to have some additional resource arc, whether it's 2 before 3 or 3 before 2. Okay? So in a way, if we would predict to our customer that we are finishing this project after 4 days, well, if you look at the bottom schedule, only if activity 2 or 3 are taking at least a period longer would we deviate from the finish time of activity 4. But if either activity 1 or 4, or combination of it, takes 1 day longer, there is no problem. While on the top one, if activity 2 or 3, as before, but also if activity 1 takes 1 period longer, you would lengthen the project, so violating the constraint of 4 days. Okay, so I hope you see this. Now, of course, you can introduce a time buffers, which is happening on the next slide. Same example. What we could do is, well, if we want to be sure that the day that we are promising to our customer is not violated, okay, we can introduce some time buffers. For instance, if we schedule activities 3 and 4 a little bit later, and even if we are scheduling the promised due date, starting time of the dummy end activity in project scheduling terms, even 1 day later, then we see that even if all activities take 1 day more than predicted, than the 2 or the 1 for activity 4, then we still have a schedule which finishes in time. Okay? And you already have to have very strange combination of the duration of the different activities to not be able to finish this in time. So this provides quite some robustness. Okay. Now what we want to do is to move on to the proactive reactive RCPSP. Proactive reactive RCPSP is where we are looking for a proactive reactive policy. Meaning, on the one hand, we want to have a baseline schedule. We want to be able to tell our customer we are planning to finish on that day. We will deliver our project to you on that day, but also all in between activities. So if we have a subcontractor working for us, we want to be able, you have to come in this week. Or if you are renting heavy equipment, then we want to do this in a particular period, being relatively sure that we can stick to it and that we don't have to change things. Okay? However, as just mentioned, it will happen that sometimes durations take longer, there will be other things happening. At that time, we want to have the best possible continuation of where we are. Okay? And we want to have a combination of that. Okay. Objective function, well, typically you want to have some cost of the baseline schedule. You want to finish your project as early as possible, or at least deliver it as early as possible to the customer. Certainly, if you are bidding for a project, that's certainly worthwhile. And any non-decreasing function of the completion time of the project, predicted completion time of the project would work. Here we are, for simplicity, using typically a linear function. we just have a parameter WB, the weight of the baseline schedule, multiplied by the length of the project. S is the starting time of the dummy end activity, which indicates the completion time of the project. That's one part. Okay. Second part being, every time that we have to react, every time that we find out that our schedule does not work anymore, then we have to react. And typically there is some cost of reaction, so WR is the wait for a reaction. Some administrative cost, we have to pick up the telephone, we have to talk to people in order to rearrange things. And then what we also do is for each activity, whenever there is a change in the starting time, so the original starting time and the new starting time, we take the absolute difference and we multiply it by a corresponding weight. Some activities are easier to organize. If these are operators within your company, well, if you tell them, well, come tomorrow instead of today, that's not too hard. But again, if I take the example of renting the heavy equipment, or you have this one of the subcontractor, it might be more difficult to rearrange things. So this will be at a higher weight. And typically also, we will have a very high weight for the dummy end activity because we want to stick to our schedule. Okay, so we want to, as much as possible, deliver our project as planned. Okay, so that's a principle. Now I will show you a couple of examples to try to illustrate and try to give you some insight into the problem and how it can be solved. So first example is in fact an unconstrained one, although there are resource constraints, but an availability of one is indicated, but all the activities are in series and they require a resource requirement of 1. Here you see activity 3 having a deterministic duration of 2, okay, dummy end activity, and these have a weight for the activity of 20 and 40. So whenever we need to change the starting time of these activities, we have to pay 20 or 40 to do so, per unit that we are changing. Moreover, we have a reaction cost on top there, which is 20. So the administrative cost, purely the fact that we have to change things, is a cost of 20. Okay. And then in this example, we have two stochastic activities. Activity 1 with 30% probability of having a duration of 1 and a 70 of 2. And then activity 2, the opposite, a 70% probability of duration of 1 and a 30% probability of duration of 2. Okay? And we want to find the optimal PR policy for this one. Now, this would be a very conservative schedule, but it's a feasible one. So here we schedule activity 1 at time 0, okay? Activity 2 at time 2, activity 3 at time 4, and the dummy end activity at time 6. And we are sure that we can always keep to this schedule. By the way, you see the arrows that you have here. These are indicating the possible lengthening of the duration of the activity with the corresponding probability. So the 70% probability that activity 1 is taking 2 time periods, and a 30% probability that activity 2 is taking 2 periods. Okay? Here, simple cost calculation, 300, because we have a predicted completion time of 6, multiplied by the baseline weight of 50, so that's 300. So that's it. However, other schedules are possible. The first or alternative one is where we schedule activity 3 and the dummy end activity 1 period to the left. Okay? This way, we might have a problem because if activity 2 takes 2 time periods, 30% probability, then we will have to change. We have to change, well, into this last schedule. Okay? We can also schedule activity 2 to the left. Okay? Might not look so nice because it's a 70% probability that this will not hold, but okay, it's a possible schedule. And lastly, we can be very optimistic and schedule everything as early as possible and try to work from that one. Okay? Now, as mentioned, these are, or not mentioned, so these are lengths of 4, 5, 5, and 6. So we'll multiply with the baseline weight of 50. So we start out with a cost of 200, 250, 2 times, or 300. And we have also the reaction cost if we have to switch between schedules, and I've named them now A, B, C, and D, okay, from most optimistic to the most pessimistic one. Then we have additional cost as mentioned before. So here, if we switch from schedule A to B, then you see that activity 3 is delayed, 1 period, and also the dummy end activity is delayed for 1 period. So we incur the reaction cost of 20, the WR, but we also incur a cost of 20 for activity 3 to be scaled 1 period later, that's the one here, and additional 40 for the dummy end activity. So in total, we have a cost of 80. And it's relatively easy to see all these costs that are occurring. Okay? So having these costs now, we can think of what is the best policy in this relatively simple case. Okay? So here, for remembrance, you have the calculation that we just saw on the previous slide. So I look at the first policy, which is the pessimistic policy, is policy D. As I mentioned, a cost of 300, and there cannot be any additional cost because we can always start activity 2 at time 2, activity 3 at time 3, and activity 4 at time, at 3 at 4, and activity 4 at time 6. Perfect. Cost of 300. If we start out with activities with schedule C, then we have a problem because we see immediately in this representation that this arrow overlaps with activity 3. So there is a 30% probability that activity 3 cannot start because activity 2 is still ongoing if it has a duration of 2. Okay? So that's what you see here. We have a 30% probability that we might have to switch from schedule C to schedule D because that would solve the problem. If we delay activity 3, but also if we delay the dummy end activity, then we will make it feasible. In the table that we had here, you see that the cost of shifting from schedule C to schedule D is 80. So we have a 30% probability of an extra cost of 80, which is 24 in expectation. So added to the 250 that we had as the baseline cost brings us at a total cost of 274, which is cheaper, which is better already. Can we look further? Well, if you look at schedule B, well, there is only one possible problem that we might have here, is if at time 1 it turns out that activity 1 takes 2 periods, 70% probability. At that time, we have to switch to a new schedule. But now we can switch to either schedule C or schedule D. So if we schedule to D, then you see the cost B to D has a cost of 80. So we have a 70% probability of an additional cost of 80, which is 56, added to the baseline cost of 250 is a cost of 306. But also, we could switch to schedule C, okay? Then we have a 70% probability that we have to switch at a cost of 20, as you see here. But then if we switch to C, we might have additionally the problem that at time 3 it turns out that activity 2 takes longer. So then this happens with a 30% probability, and then we have to switch to D anyhow. This 30% probability is on top of the 70% probability that we are already switching. So we have to multiply these two. That's a 21% probability at a cost of 80, as indicated here. Okay. So if you calculate this values to 280.8. Okay, so with A, it's a little bit more complicated because then you see already in the representation that you have two possibilities of overlap, namely with activity 1 and 2 and between activity 2 and 3. Okay? In the first case, so with a 70% probability, we cannot scale activity 2 at time 1, so we have to switch to either C or D. Here, D is represented. Later on, you will see the C. This happens to be at a very high cost. Switching from A to D is at 140, so 70%, that evaluates to 98. But also, even in the case that activity 1 takes only one time period, 30% probability, we can start activity 2 at that time, but then we still have a 30% probability that activity 2 will take longer and that we cannot start activity 3 at time 2. So again, multiplying this, you have a 9% probability, 1 minus 70%, so 30% multiplied with 30%, 9% probability, switching from A to B at a cost of 80. If you add all these costs, it evaluates to 305.2. And lastly, you could also switch from A to C, but then again, here, as we have seen before already, at that time, it might be necessary to switch to D again. And if you see the cost calculations, then it evaluates to 280. So in this case, these are the 6 possible policies that we have. These are relatively manageable, okay? And we just take the cheapest one of them. So here it's clear that C, possibly switching to D, is the optimal policy. I say optimal, but there is a slight remark I have to make on this. Because we could do a little bit better than this. What we could do is the following. If we start out with schedule C first, okay, we just progress. At time 1, okay, we can see whether activity 1 is finished or not. This brings new information. If activity 1 is finished at time 1, 30% probability, then we could switch to schedule B, okay? We schedule activity 2 earlier, and then you see we don't have any problem after it, because at that time we know that activity 1 takes 1, okay? We have a 30% probability that we switch between C and B, as only activity 2 is changed in starting time. That's of course why we have a weight for activity 2 at 0. There is no additional cost, okay? So only an expected cost of 6 is added. However, if activity 1 takes 2 time periods, then we stick to the plan for schedule C. We schedule activity 2 to start, and then we still have a 30% probability that activity 3 cannot start at time 3, that we have to delay it, namely to schedule D. This 30% has to be multiplied with the 70% that we have here, so it's 21%. And if you now calculate the total cost, the baseline is 250 plus 6 plus 16.8, that's 272.8. This is slightly cheap. This is the optimal, what we call conflict-based one. And in the explanation I gave you before, I always mentioned whenever there's a distortion, we react. However, this is really the optimal one, but here we are reacting at a time, or certainly in the first case, where we don't have a distortion. We still can schedule activity 2 at time 2, and we can perfectly execute the project. So, problem is, if we have, well, this is of course only 2 possible durations. If we would have 10 possible durations for each activity, then at each possible time we have to check, and we have so many reactions that are possible. Moreover, typically it turns out that this does not produce better results than the conflict-based ones. My PhD student Morteza Davari had to construct this example in order to illustrate that it's possible that you have non-conflict-based reactions which are possibly better than the conflict-based ones. Okay. This is the unconstrained case. If we switch to the constrained case, second example, similar one. Now we have some presence relations between the activities, but we have also resource requirements, 1 for activity 1 and 2, and 2 for activities 3 and 4. Again, on top you see the distributions. I try to make it as simple as possible to remember. So it's always a duration of 1 or 2, and the probability of having a longer duration matches the number of the activity. So it's 10% for activity 1, 20% for activity 2, 30% for activity 3, and 40% for activity 4. Also, I made, because it doesn't matter too much in this exercise, the weights for the corresponding activities equal to the number of activities. So 1 for activity 1, 2 for activity 2, 3 for activity 3, and 4 for activity 4. Moreover, you see the resource requirements, I mentioned already. So 1 for activities 1 and 2, and 2 for activities 3. Okay. Now again, we can consider the minimum forbidden sets. So if we first look at activities 1, 2, and 4, there is no presence relation in between them, so they are potential for minimum forbidden set. They have a requirement of 1 plus 1 plus 2 is 4, availability is 3, so indeed this is a minimum forbidden set. You cannot eliminate one activity and still have a forbidden set. If you look at the other side, activity 1, 3, and 4, requiring 1 plus 2 plus 2 is 5 units, only 3 are available. Well, in this case, we can eliminate activity 1, and activities 3 and 4 requiring 2 plus 2 is 4 units still violate the resource constraint. So we cannot schedule them together. So that's the forbidden set 3. As I mentioned before, in the other example, we can solve the problem, eliminate the resource constraints in a way by solving all of these minimum forbidden sets. Well, if we start with the last one, minimum forbidden set being 3 and 4, we have two possible ways of solving it, either 3 before 4 or 4 before 3. Let's start with the first one, 3 before 4. Then we have this schedule, and you immediately see that at the same time, we are also solving the other minimum forbidden set. Because we have 1, 2, 4, but 2 is already a predecessor of activity 3. And as we say now, 3 before 4, transitively, 2 is also before 4. So it solves this minimum forbidden set. So this is a potential, well, again, pessimistic schedule that we have. In the other case, if we have 4 before 3, then we have 3 possibilities, namely these 3, where on the one hand, we are also solving the minimum forbidden set 1 to 4 by delaying activity 1, here by delaying activity 2, and here by delaying activity 4. If you look in this example, you don't have, well, you have to wait until only one other activity is finished. So activity 1 has to be delayed, but as soon as activity 2 or 4 is finished, we could start activity 1. Okay? Same here for activity 2. As soon as one of them is finished, we can start it, and the same here. Okay? So here again, 3 pessimistic ones. You clearly see that this one has the best perspective, the one on top. Even if we are looking at it pessimistically, we have a duration of 4 only. In the other cases, we have 6. So let's analyze this one a little bit more carefully. So here again, you have the information. This was the very pessimistic scale that I looked at. Now I can enumerate a number of them, and you see F, so it means that there are 6 possible scales. So the next scale could be where the dummy end activity is scaled 1 period earlier, okay, at time 3. The next one is where activity 1 is scaled earlier. Remember, I just said this activity has to wait until either activity 2 or 4 is finished. Activity 3, because of the presence relation 2 before 3, because of the resource arc 4 before 3, has to wait until both are finished. Okay, so in that way it makes a difference between them. And also a combination of the two, where one is scaled earlier, but also the dummy end is scaled earlier. And lastly, the optimistic cases, where 1 and 3 are scaled immediately after activities 2 and 4 in the shortest duration, but with project length of 3, and then also with a project length of 2. These are all the combinations. Easily now, again, to calculate the corresponding transitions, the transition cost, okay? So for instance, if we switch between A and B, then what you see is that we only are delaying the dummy end activity. So we have a cost of reaction of 20, but we also are delaying the dummy end activity with 1 time period, so we have 20 plus 40 is a cost of 60. So you can easily, and I checked them, double checked them, so I hope these are all, I think they are all correct. Okay. Now again, having this information, we can look at the potential policy that we have. Again, the pessimistic one, schedule F, starting at a cost of 200 because we have a deadline, or we have a completion time of 4, multiplied with 50 is 200. That's simple. It's always feasible. We can execute this. If we start with schedule E, then there is some probability that we cannot hold on to the completion time of the project. Namely, if activity 1 or 3 is finishing later than the predicted time of 1, so at time 3. What is this probability? Well, you can look at the probability that both activities 1 and 3 are finishing at time 3. That's a 90% times a 70% probability, so that's 63%. So not finishing at time 3 is just a complement of it, 37%. Okay? So you see the 37% multiplied by the cost that we have of changing from schedule E to schedule F, which is 60. So it turns out to be 172.2. Okay? If you look at schedule D for starters, okay, already the representation tells you here that there might be a problem when activity 1 cannot be started on time. As I mentioned before, this is only possible when both activity 2 and 4 are not finishing at time 1, which is just a multiplication of 20 and 40%, so that's 8% probability. So that's what you see here. So this brings it at the cost of 201.68. Okay. Alternatively, we can switch from scale D to E, which might seem a little bit strange because we are delaying activity 1 on the one hand, but then we are setting the deadline earlier, okay, which is a stupid one perhaps in a way. It's a possibility, so that's the probability that we have here with the corresponding cost. But then, of course, you see in this case, the 37% I mentioned earlier, multiplied with the 8% that we already have to get into the situation, leads up to 2.96% cost that we need to change to schedule F. Okay. It also makes sense that it's a more expensive cost. Okay. Then we have a start with schedule C. Well, again, the representation shows that on the one hand, you might have a problem for scheduling activity 1, but also you might be scheduling, well, the dummy end activity, so there might be a violation there. So that's the two possible ways that we have to get out of it. If activity 1 cannot be started at time 1, because both 2 and 4 take longer than predicted, the 8% probability again, then we have to switch to either schedule F or schedule E, where 1 is scheduled in parallel with activity 3, and depending on the due date. So here, first F. And secondly, if you look at the second possibility here, where we cannot meet the project deadline that we are predicting to be 3, then we have to switch to schedule D. Okay, again, the corresponding cost, it's a 30% probability times the 92% complement of the 8% that we have here. So if you see the cost 171. Alternatively, we can also switch to E and then to F, if sometimes necessary, okay, and then bring this cost. Next, if we look at schedule B, okay, then again we have the 8% probability that we have to delay both of them, activity 1 and 3, because because both 2 and 4 are taking longer. So this is this cost. But also, it's a possibility that we only have to delay activity 3. So, yeah, this one was scheduling to either F or E. In the case that activity 3 has to be delayed, we are shifting to schedule C or D. And now you see the 4 combination of them, either switching to F for the first one, or to E, and then later to F, or switching to D, or switching to C, and then later to D. I will not go into all calculations, but you see the logic of it, so you see the involved cost. And lastly, for activity A, we have 3 possible deviations, distortions, namely one where activity 1 has to be delayed, one where both 1 and 3 has to be delayed, and one where the dummy end activity has to be delayed. Okay? In the first case, okay, the 8% probability where both activities 2 and 4 take 2 time periods, then we have to switch to E or F, one of these, okay, because when schedule 1 and 3 time to start at time 2. In the second case, I have to explain, because we have an 80 times 60% probability that both activities 2 and 4 finish at time 1. That's the 48. So the complement is a 44, where either activity 2 takes 1 period longer or 4 takes 1 period longer. And then we have to switch to D or C. So you have the 4 combinations again, and again you can do the calculations. I will not go into detail, but then you can see the cost. And in this case, you will see that the cost is, well, perhaps one of the most complex policies, but is the lowest cost, so it's beneficial. Okay? I hope you are still following the procedure, and you might think, well, it's not too difficult to solve. But in fact, these are lots of possibilities that you have to consider. Here we are only looking at 2 possible durations for a number of activities. In reality, it explodes enormously. So this is not the way how we are solving these problems, but I hope you have the setting of the problem. So the last part of the presentation, I will be showing an example where it indicates how we are solving the problem. Okay. So here, I'm looking at a more general problem. So where you have 8 real activities, a dummy start and a dummy end. On this slide, you see the resource requirement for each of the activities. And for instance, and please remember this, if you look at activities 1, 2, and 4, together they require 2 plus 3 plus 4 is 9 units. And it indicates on top that only 8 units are available. So it's some kind of minimum forbidden set. We cannot scale them all at the same time. Okay. On the next slide, you see the durations, but they are stochastic durations, and now a little bit more general than before. Not only 1 or 2, but different durations with the corresponding probability. If you look at them, there are 5 activities here which have 2 possible durations, and 3 of them have 3 possible durations, leading to a total of 864 combinations. Okay. And just to focus the attention, one possible combination could be the one which is indicated in bold. I hope you see it, where the durations, as mentioned below, 2 for activity 1, 8 for activity 2, 3 for activity 3, and so on. If we are assuming that these durations are independently distributed, we can just multiply probabilities. So this occurs in 0.054% of all cases. Okay. We will be using this one. Okay, that's the first step. So that's the information that we have. Now, what we want to do in order to solve the problem is to look at a number of schedules. So we will create, in a particular way, a number of schedules. And then we will try to have, or we will make sure that we have a Markov decision process for all the schedules that we are considering. Okay? So for instance, Morteza created 10 different schedules here in a particular way for this problem. These are all feasible schedules. Feasible, at least with regard to the minimum duration of the activities. Okay? That's a different definition of feasible in a way. And now it's possible that so let's say we start with schedule 1, okay, with the corresponding starting times from activity 1, dummy start, to activity 10, dummy end. Okay. And now we see it's indicated in red. Why? Because it's infeasible. It's infeasible if you would have this realization that I just mentioned before. You see here that activity 1 has a duration of 2, which is a possibility. You see that we are starting the project first with activities 1 and 4. These are started at time 0, but we were planning to execute activity 2 at time 1. However, that's the schedule that we have below. If activity 1 takes 1 period longer, it overlaps with the starting time of activity 2. And remember, activities 1, 2, and 4 were a minimum forbidden set. So you could not schedule them in parallel. So you cannot keep on to this schedule, so you will have to shift to another schedule. For instance, this example here to schedule 9 is the following one, where you see activity 2 is planned at time 2, and this would allow the schedule at the moment. Okay. Of course, there's a probability that activity 1 will take 3 time periods. At that time, we will have to reschedule again. Pity, but that's the case. Okay. Now, how do we create this Markov decision process? Well, we need to indicate the state of the project. So we need to know, with the least possible information, where we are in the schedule. Okay? Where we perfectly know everything about what we have executed so far in the schedule. One possible way, not the best way, but the simplest way, is this one, where we know which schedule we are considering. So remember, a schedule indicates all the starting times of all the activities. Okay? So we know when the activities are planned and when they are executed. T indicates the time at which we are considering the state. O is the ongoing activities, set of ongoing activities. So at that time, we know which activities which were scheduled in the past were already finished, but also the ones which are still remaining. And we already know how long they will take, because we know the starting time, and we know they are still ongoing at this moment. So we still have some information about how long it will take, or what the distribution is of this. And lastly, the number of reactions. So this is one possible way. If we have this information, we are perfectly aware of where we are in the network, or in the progress of the project, I would say, and we can work on this. Okay. An example to illustrate. So again, we take schedule 1. This is the corresponding starting times. Here we are using the minimum durations for each of the activities. So if we now look at time 1, okay, and if we assume that activity 1 really took only one time period to execute, okay, then we see at that time we have schedule 1, namely the set of starting times that you are indicated. We are looking at time period 1. Only activity 4 is ongoing, okay, and we had no reaction so far. This perfectly tells us, so activity 4 is still ongoing, and our schedule is indicating that activity 2 will be starting, and we know the remaining distribution of the duration of these activities. Okay. Now we need two kinds of reactions in order to construct a Markov decision process. The first one is a chance transition, where we start the Markov decision process with each of the schedules. So if we have the 10 schedules I indicated before, we have the 10 schedules. We start at time 0 with no ongoing activities and 0 reactions so far. This is, for instance, schedule 1. And we move one time period further. Okay? If we do so, what we know is that, well, activity 4 with this distribution, so a 10% probability of a duration of 3, 50% probability of a duration of 4, and 40% probability of a duration of 5, we know that activity 4 will still be continuing at time 1. It has a duration of at least 3. However, for activity 1, it's slightly different because we have a 40% probability of having a duration of 1, and then 40 and 20 for 2 and 3. So there is a 60% probability that activity 1 will still be ongoing at time 1. So we will move from this state to two possible states, a 40% probability that we move to the state where activity 1 is finished, and only activity 4 is ongoing, okay? And then a 60% probability, the remainder here, where we move to a state where at time 1, activities 1 and 4 are ongoing, okay? So in the first case, it's indicated in green, we just can continue the schedule, no problem. In the second case, it's indicated in red, we have to react. How can we do so? By switching to a different schedule, okay? For instance, this one. But we have to make sure that the starting times of all the finished activities and the ongoing activities are remaining the same. We cannot go back in time and change these starting times, so we have to keep to that. Only for the unscheduled activities, we need to have at least one which is changed, because otherwise there is no reason to change. Okay? So if we look at the example here, so this is the infeasible state. If we now look at, so we're starting from schedule 1. If we now look at all the other schedules, 9 other schedules, you see that schedule 3, 6, and 10 has different starting times for activities 3, so for activities 4, for activity 4. So we cannot choose them. Moreover, the problem that we have, namely that we cannot start activity 2 at time 1, because activity 1 takes longer, is identical in schedules 2 and 4. So only the 4 remaining ones, 5, 7, 8, and 9, are remaining. So we should switch from the infeasible state to feasible states where we have a different schedule. We look at the same time, we have the same ongoing activities, okay, because otherwise we are changing the past. And now we have run reaction, so we have some reaction cost involved. Okay? If we do so, then we create a Markov decision process like this. It should be a tree, but for representation purposes, it's collapsed a little bit. Okay, so whenever there were two states which were identical, although they were reached in a different way, they were drawn. But in fact, it's a tree behind this. Okay, and you see the green is indicating all the feasible states, the red is indicating the infeasible states, which have to be adjusted. And the ones in brighter colors, brighter green and brighter red, are the optimal policy. Okay, so this creates the optimal policy in a totally different way than I just explained before, but which is impossible in this case because there are too many possibilities. Okay? I will not go into the problem. I just mentioned there is one problem here. In this case, we only had 10 schedules, so it's perfectly possible that at some time, if we have a conflict, we have to react, that we don't have a schedule which for the already finished activities and ongoing activities has the same starting times. So that's a grayish color that you have here. We call this a dead chain. Here we then cannot continue. But in fact, there are simple ways and we have a different representation where you can easily overcome this problem. So no, it's not really a problem. But just for explaining purposes, I use this example. So I will not go through this one, but perhaps just the last one. Here we see a reaction from this infeasible state to this feasible one. It just indicates, well, don't bother about the numbers, but this is schedule 9, okay? At time 2, where activities 1 and 4 are ongoing, so binary notation, but don't bother, and where there was no reaction, which was infeasible, and reacted to schedule 8, which you see at the bottom, where, again, at time 2, activities 1 and 4 were ongoing, and there was one reaction. The reaction cost is indicated here, so we look at the changes in the starting times of each of the activities multiplied by their weight, plus the reaction cost of 20, which evaluates to 53. And then you see you just perform dynamic programming, where the cost here is 612.8. We add the 53, and then we come at the cost of 665.8. It was an optimal reaction, so the two other ways that you went out of it had a more expensive cost. So I just look at this. So I hope this gives you some indication of how this can be solved. So I would say the PR-RCPSP, I hope I showed a little bit that you can solve this using a Markov decision process. And in fact, the RCPSP is a quite general problem, project scaling problem. It's only activities with presence relations, resource requirements, and you can have many other scaling problems which are being represented by this one. Don't bother about the dead chain, as I just mentioned. There are other models that can solve this. If you look at, for instance, 2,000 schedules, then within 5 minutes you can solve this Markov decision process. So you can have the optimal solution, which is already relatively good. It gives the optimal solution, but only with regard to the given schedules. So what we are doing as research now, one of my PhD students is looking at how can create a different set of schedules so that we have a better cost, a cheaper cost for this overall policy. And as I mentioned, as it is a quite general problem, there are other scheduling problems. I'm also working in operating room scheduling, as Christos has said. And you can also have the same idea also in these other scheduling problems and try to apply this to find the best solution. That was the end of my talk. Thank you.
Thank you, Erik. And I forgot to mention at the beginning of the talk that this talk was sponsored, and Erik has been sponsored by Euro. So it was the Euro Plenary talk, and we thank Euro very much for their sponsorship. We have time for one quick question, perhaps? Yes, please. Yeah, I think we can hear you. But...
Okay, so I wondered whether you consider the case where you have people with different levels of skill or expertise or speciality, when the more experienced people can do multiple tasks.
Yeah.
I'm not aware of this, right?
We did not do any research on this yet, but as this problem is indeed a generalization of RCPSP, so you can work with the different resources. So here I always used only one resource type. There can be plenty of resource types. You can even work with different specialties and so on. So it's perfectly possible, but it's not included in this research, no.
All right,
no,
thank
it's certainly a valid one. And again, as I mentioned, the ideas are similar, but you can apply this. Yeah.
Thank you.
And there was one hand right behind you, if I remember well. And we have the microphone.
Hi. I had a very specific kind of nitpicky question about what your second set of examples, which is when you had the two sets of two tasks in parallel, and you had the 6 schedules. There was only one pair of scenarios in which the second pair of tasks were offset, and they were both offset the same way. And I was wondering what the justification for that being the way round it was, because it seemed to me you might get it slightly faster the other way round. Yeah, sorry, it's probably best you go all the way back to it. But
I did not...
Yeah, so for these ones, schedules C and D have the second pair of tasks offset, but the green one is always later.
Yeah.
And if you're transitioning from A or B, and it's the yellow task that is delayed and not the blue task, wouldn't it be better to, instead of having to switch to tasks E or F, to schedules E or F, to switch to some analogy of C or D in which the, that's probably a better one to look
Yeah,
at,
okay,
in
also-
which the green and red tasks are the other way around.
No, but because you have the problem on the one hand that you have 2 before 3 as a presence relation, but in order to solve the minimum forbidden set here, you also have 3 before 4.
Okay, yes,
so-
no, fine, fair enough, yes.
So both have to be valid, and then therefore you have this
Yes.
difference. Yeah.
I had forgotten the diamond diagram by the time we were on the next slide. Sorry, my bad.
Perfectly understandable. Yeah. Okay. Thank
Well, just
you.
for attention to detail, I have
But,
to.
no, but good question.
Okay, I'm afraid this is the time that we had. So thank you very much again, Erik. And